Hello everyone, I'm Mehmet Öztürk from Electrical and Computer Engineering at North Carolina State University. In this lecture, we'll be discussing nanoscale heat transfer. And our goal will be to understand how heat transfer occurs in different materials. To do this, we'll be looking at heat from a nanoscale perspective. We'll be looking at atoms, molecules, photons, nanoscale objects, that is, to understand heat transfer, and then we'll apply this to explain macroscopic properties of heat. We will conclude our discussion with some applications of heat transfer. Let's begin by defining heat. Here is how I like to define heat. Heat is traveling energy of moving things. So there are two things that I need to highlight here. So let's use our red pen. First, there's some energy involved, but it's not just any energy. We're not looking at some lump sum of energy. This energy is traveling energy. So our energy is moving from point A to point B. There's some flow of energy. Second, this is not just any energy, but it is the energy of moving things. So some objects are moving. So we'll be talking about these objects. What are they and how are they moving? I'd like to begin by giving a physical meaning to temperature. To do that, I'd like to consider a confined box filled with some gas. So inside this box, I have nothing but the molecules of this gas in random motion. I'll also assume that the temperature of this box is 300 Kelvin, so it's sitting at room temperature. So what do I mean when I say the box is sitting at room temperature? Well, what I'm trying to do is I'm trying to quantify the average energy of these molecules, or average kinetic energy of the molecules, or average velocity of these molecules. So let's be sure. The energy of a molecule is measured in joules. Temperature is given in Celsius or Kelvin. So temperature is not energy, but it's a means to energy. I can use the temperature of the molecules of this box to calculate their average velocity or average kinetic energy. So I say average because these molecules are not completely free. Although they have a lot of space around them, they cannot travel forever before they run into each other. So they go through these collision events. And when they collide, they sometimes lose, sometimes gain energy. So their energy is going back and forth. It's constantly being exchanged during these collisions. But because this is a confined box, the number of molecules inside this box is not changing. So the energy is not going anywhere unless I provide some heat from outside to increase their average energy. But as long as I don't do that, the box stays at 300 Kelvin, the net energy of the box, the net energy of the molecules will remain the same. Okay, so in summary, temperature is essentially something that I can use to calculate the energy of these molecules. And in fact, as we shall see, temperature and energy are directly related to each other. So now let's use this to talk about heat. And to do that, I will construct a thought experiment. And in this experiment, I will again use a box. And again, I will fill my box with some nice gas molecules. And I will start with a uniform temperature. Again, I will say that this temperature is 300 Kelvin, but more importantly, the temperature of this box is uniform. So when I look at the average velocity, average energy of these molecules anywhere in this box, I will find about the same energy. Then I will add a heater and heat the box only from one side. So heat will flow to the left side of the box. And for the time being, let's assume that the walls of this box can take this heat and pass it onto the molecules without any obstruction. So let's just say that this energy, this heat, can penetrate through the walls and molecules can absorb them. What's going to happen is that the molecules closer to the walls of the box will be the first ones to absorb this energy. So right at this point, the velocity of these molecules will be more. So these molecules will be a lot more energetic than the molecules on the right side. Okay, so let's call this the high temperature side, and let's call this the low temperature side. Now, so of course these molecules are going through these collision events, but now what's happening is that the molecules closer to the hot wall, because they are more energetic, when they collide with molecules to their right, they have more energy to give to them. So slowly but surely, these hot molecules will be transferring some of their new energy to the molecules on their right. And that energy will be slowly moving molecule by molecule from left to right. And I think you can imagine the flow of this energy through these collisions slowly reaching the cold side of the box. So what we are referring to here, or what we are trying to describe, is that there is this energy moving. There's this kinetic energy moving. And this kinetic energy is moving because these molecules are physically interacting with each other. They're colliding. But because we have a constant source of heat on the left, the molecules on the left side of any collision event are likely to be more energetic than the molecules on the right side of that collision. So energy is always going from left to right. But overall, we can say that on the average, there is some energy motion. Now, this doesn't mean the molecules themselves are moving from left to right, but their energy is moving through these collision events. This motion of energy, this traveling energy, is what we refer to as heat. So going back to our first sentence, when we started our discussion, heat involves energy, but heat is not just energy, it's traveling energy. It has to move from point A to point B. And it involves some particles. And in this case, those particles are molecules. But as we shall see, there are other forms of transporting energy. It's not just molecules. This is the case for a gas, and it does make sense. But I could construct a very similar scenario using electrons in a system, in a conductor, for instance. So we have particles interacting with each other, and these interactions, in this example again, are collisions. But as we shall see, there are other forms of interactions as well. But nevertheless, they are interacting with each other, and through these interactions, energy is transported from one point to another. So traveling energy, and we have particles somehow communicating with each other for this to happen. So that's heat. Okay, so let's now consider our box again. And again, our box is filled with some gas. And it's sitting at some uniform temperature. I'll add a little bit more information about our box. Suppose we know the pressure inside this box. So pressure P. And I know the volume of this box. That's the volume. So what is this pressure times volume product? Does this have a physical meaning? I think this is worth looking into more closely. So first of all, pressure is force per unit area. So in the MKS system, this will have the units of Newton per meter square. And obviously, the unit of volume will be meter cube. So this product will be Newton times meter. This is interesting because Newton is force, meter is distance. So what I'm really saying is that PV is equal to force times distance, which is really equal to work, which is also known as energy. So, pressure times volume is referring to the energy of the molecules confined in this box. Great. So, I just said that I can use the temperature of these molecules to refer to quantify their kinetic energy. Now I'm relating that energy to pressure inside the box. And what is pressure? Well, our gas molecules are constantly colliding with the walls of the box. And with each collision, these molecules are applying tiny forces on the walls. So pressure is basically a collection of all these tiny forces applied by the molecules on the walls of the box. Okay, so we know what PV is. Pressure times volume is equal to energy. But we should remember another very familiar equation. That is, PV is equal to N times R times T. This is very exciting. We said that pressure times volume is equal to energy, but a few moments ago, we claimed that energy and temperature are related. And here we go. We had that relationship all along. Well, in this equation, we have these two constants. Let's remember what they are. N is the number of moles, defined as the number of molecules divided by the Avogadro's number, and R is the universal gas constant. So assuming assuming that you know the number of molecules inside the box, we can calculate the number of moles. Great. So I can write my equation PV equals nRT in terms of the Avogadro's number, n divided by n sub a times RT. Since I know the number of molecules n inside the box, I can also be interested in finding the average energy of a single molecule inside the box. And to do that, all I have to do is divide the total energy by the number of molecules inside the box. So if I divide both sides of this equation by n, the left-hand side will give me the total energy, P times V divided by n. So that's the number of, or energy per molecule. And if I divide the right-hand side by the same constant n, we will have this n canceling out with this n. And in the end, I'll be getting R, the universal gas constant, divided by the Avogadro's number times temperature. So this is exciting. Why? Because this ratio of R to n sub a has a very special name. And this ratio is nothing but the Boltzmann constant. So what we are really saying is here is very special. We are saying that if you have a particle, let's say this is a molecule, the average energy of that particle is approximately equal to Boltzmann constant times temperature. This equation is worth a new page. So energy of this molecule is approximately equal to the Boltzmann constant times temperature. Okay? And this turns out to be true for other particles or other carriers of heat as well.